Let's talk about some integrals that involve trig functions, and there's basically some forms to look at. And the first type we're going to look at involves sine and cosine, and either one or both functions, sine and cosine, are raised to odd powers. So for instance, this one's sort of ready to go in that it's got this loner, as I like to call it, cosine. And so this one, pretty straightforward in that the way to go is to let u equal, do a u substitution, let u equal the sine of x, right? And of course the derivative then is cosine of x dx. And then the substitution du takes care of both the cosine of x and the dx. Since u is sine, u to the fifth replaces sine to the fifth of x. We integrate. I didn't write it down here, but of course that's 1/6 u to the sixth, right? And then we back substitute to get the answer. Let's try it again. This time, notice that we don't have sine and cosine. We've got sine to the fifth. And notice what I can do with this. I can peel, because it's an odd power, I can peel a sine off as what I call a loner. Now we've got sine to the fourth, but sine to the fourth can be expressed as sine squared times sine squared. Now recall that identity sine squared x plus cosine squared x equals 1. Well, sine squared x therefore must be the same thing as 1 minus cosine squared x. So in this next step, that's what I've done. I've taken the sine squared out and I've replaced it with 1 minus cosine squared. So now over here in the box I've said, how about letting my loner be involve the sine, and I'm going to let u equal the cosine of x. If I let u equal the cosine of x, it implies the derivative is negative sine x, right? And if I need the sine x, the loner, I'm going to say sine x dx is the same thing as negative du. So I'm going to put my negative du in down here, and negative du takes the place of the sine x, right? And then I'm going to have a 1 minus u squared, but I've got two of them, so I just put the square on the outside. Then I expanded, right? 1 minus u squared. Expanding that is going to be 1 minus 2u squared plus u to the fourth. I'll integrate. I'll get a negative u plus 2 times u cubed over 3. And then won't it be a minus u to the fifth over 5, and then I'll back substitute, right? My u is cosine x, so I'll put the cosine cubed, cosine to the fifth, and there it is, right? We've got another example. One more time. Again with an odd power, and so I'm always looking for the odd power, and I'm going to peel one off. So I'm going to peel one off, and I'm already thinking about, cosine x dx. I'll let that be du, and let u be the sine of x. You might say, well, wait a minute now. I've got this cosine squared x, but can I use that Pythagorean identity again and say it's 1 minus sine squared x? So I've got, if u is sine, I've got u to the sixth, 1 minus u squared, and my cosine x dx is my du, right? So I'll multiply through by the u to the sixth. I'll evaluate. u to the 7th over 7, u to the 9th over 9, and then back substitute, and I've got my final answer. When you're watching the video, you might want to pause and just study over what I've done in the steps, but these first three, I think I've got them pretty straightforward for you. Let's take a look at what happens when we have evens. M and N are even. And over here in the box, I've kind of put the hint over here. And these are using these so-called half-angle formulas for cosine squared and sine squared. So the problem, and this problem is very much like number 6 in the book. It isn't exactly like 6 because 6 has some upper and lower limits, so it needs to be evaluated. But basically what we're going to do is we're going to take the sine squared x out, and the sine squared x is going to get replaced by, we're going to come over here, right, and take the 1/2, the quantity 1 minus cosine 2x, and then we're going to do the same thing with the cosine squared x. We're going to take it out and replace it with 1/2 times the cosine of 1 plus the cosine of 2x. So 1/2 times 1/2 brings me the 1/4 out front, and then if I FOIL it, I get 1 minus cosine squared of the 2x. So this piece again, it's cosine squared. The argument is different now. It's 2x, but it's a square. So I'm going to use that formula from above that's in the box once again, that first one. And I'm going to take cosine squared and I'm going to turn it to 1/2 times the quantity 1 plus the cosine of twice the argument. So twice 2x makes for the 4x. So be careful here now. 1/2 times the 1 is a negative 1/2. So 1 minus a half gives us this half. And then negative 1/2 times cosine 4x, right here we are over here. We take and evaluate now. The half becomes a half x, and the integral of half cosine 4x will be a half times the sine of 4x times 1/4 because of the 4x, right? So you might want to do a simple substitution to get that. I think most of you are on board with me regarding that. And then multiply through by the 1/4, and you come to the final answer. So that one's number 6. You have an opportunity to do that one on your own and make sure that it's working for you. Let's take a look at problems, and they start with numbers 7 through 10. And I'm a little disappointed in that they say, make this substitution. I'd like you to fiddle around with them a bit on your own, but take a look here when M and N are, in this case, the powers of secant and tangent are both even. As in this example, sec to the 4th, tan to the 6th. Well, what I'm going to do here, I'm going to use this fact that, if I've got tangent, the derivative is going to be a secant squared. So I'm going to peel off a secant squared dx by itself, and then I'm going to re-express the other secant by using that trig identity that I've put up here, that's related to sine squared plus cosine squared equals 1, right? Anyway, sec squared is going to get replaced by this. Tan to the 6th is as it was, and here's that peeled off sec squared x. So now I'm going to use these relationships here, right? I'm going to use these guys and I'm going to let the u be the tan, and I'm going to let the sec squared x dx be the du, right? So that takes the place of all of that, right? And multiply through, and then evaluate and back substitute, and I've got it. U to the 9th over 9, but back substitute, remember u is tangent to the 9th x over 9, tan to the 7th x over 7 plus c. And one more time, let's take a look, see, and I'm working with, I'm on, so this time let's take the situation where they're both odd, and if you have a mixture you have to toy around with a little bit. I think it comes pretty easy. In this case we got secant is odd and tangent is odd, and I'm going to use this relationship in the bottom row here. I'm going to peel off a secant by itself, and rather I'm going to peel off a sectan by itself, and then put everything else in terms of secant. So this tangent, I'm going to use this relationship once more, but now I'm going to say tangent is, and I'm going to take this 1 to the other side here, right? And I'm going to write a minus 1 over there, and I'm going to say sec squared minus 1 is the same thing as tan squared, and then if I square it, right, I now have everything thus far in secant. I've got peeled off here a sectan, which is going to be that replacement du, and all my secants are going to now be expressed as u to the 8th rather than sec to the 8th, and sec squared is going to become u squared minus 1, and then I'll square that quantity, I'll square that out and multiply through by u to the 8th, and I'll get all this. I think I did that right. U to the 4th times u to the 8th would be u to the 12th, 2 negative 2u squared times u to the 8th, and then a positive 1. Yep, I did all that correct. And then I'm going to evaluate and back substitute my sec x, right? My sec x for the u. So there we go. We got them all in there, and we're done. So those are some examples of problems that go with numbers 1 to 10 on page 393. So that's what you should try now, is on your own go to page 393. If you don't have your book at home for some reason, you know there are the problem sets in the Google Drive, and this is section 5.7, and we're talking about 1 to 10 all. Thank you very much, and have a good afternoon. Bye now.